Training GPT-4 consumed more electricity than 1,000 average American homes use in an entire year. And training GPT-5, that consumed 10 times more. But here's the thing, that's just the training phase. Inference, which is the actual process of AI answering your questions, that runs 24 hours a day across millions of users simultaneously. By 2026, AI data centers are projected to consume electricity equivalent to the entire nation of Germany. The world is building artificial intelligence as fast as it possibly can, and it's running directly into a massive brick wall called the global power grid. Welcome to this MacroSignal explainer. Today, I'm going to show you why this collision between digital ambition and physical limits is literally one of the most important infrastructure investment stories of the decade. Every single day, forces you've never heard of are moving your money. The Fed, AI, geopolitics, currency wars. Most people only see the headlines, but they never understand the signal beneath the noise. That's what MacroSignal is for. We are here to decode those hidden forces and map out exactly how they are reshaping the world around us. If you look at the mainstream media right now, everyone is completely obsessed with chatbots, software updates, and the latest algorithmic breakthroughs. But the real story of AI, it isn't software at all. It's dirt, steel, and energy. To make generative AI an everyday reality, we have to physically build the infrastructure to support it. And as we're about to see, the sheer, unprecedented scale of this physical build-out is completely fracturing legacy supply chains.
Let's start with Section 1, the $200 billion hardware push. According to Goldman Sachs economics research, global investment in artificial intelligence is forecast to approach $200 billion by the year 2025. Now, this isn't just a bunch of venture capital flowing into some new app development. Before businesses can actually adopt AI and see those massive promised efficiency gains, a historic amount of upfront capital is required to acquire and implement the physical and digital infrastructure. Think of it like this. We're essentially building the world's most expensive plumbing system before we can even turn on the tap. Goldman Sachs breaks this massive investment wave down into 4 key segments: model developers, infrastructure suppliers, software developers, and enterprise users. Now, while early investment was heavily skewed toward the companies actually training the models, the bulk of this $200 billion wave is a massive, relentless hardware push. We are talking about building the physical data centers required to run complex AI queries at a scale we have simply never seen before. To put this into a macroeconomic perspective, Goldman Sachs projects that AI-related investment could eventually peak at 2.5 to 4% of US GDP. We've actually seen this pattern before, right? Innovations like the electric motor and the personal computer unleashed massive investment booms of around 2% of GDP as they were being adopted. AI could be even bigger. Over the next decade, this could boost global labor productivity by more than 1 percentage point a year. But to get there, we absolutely have to spend the money and physically build that infrastructure first. Which brings us to Section 2, the $7 trillion data bottleneck. McKinsey estimates that global spending on data centers could reach a staggering $7 trillion by 2030. $7 trillion. This is quite literally one of the largest infrastructure buildouts in modern human history. But there's a massive problem emerging on the ground. The traditional operating models of industrial equipment suppliers, the legacy companies making the actual physical components, are completely misaligned with the speed required by today's tech giants. The tech companies are moving at the speed of software, while their suppliers are stuck operating in the age of steel. Let's compare the two. Traditional data centers were pretty predictable. They had steady growth, predictable power demand, and honestly, you could cool the servers using basic air conditioning. But AI data centers are a totally different beast. AI workloads create sharp, violent swings in power demand. The server racks are incredibly dense, and they run so intensely hot that air cooling is no longer physically sufficient. Because of this, liquid cooling has transitioned from being a niche luxury to an absolute baseline requirement. The traditional industrial suppliers who are used to building for slow, highly regulated utilities, they simply do not know how to handle this level of volatility. And the real-world consequence of this disconnect is a devastating physical bottleneck. If you are trying to build a data center in North America right now, you're looking at lead times of 50 weeks for critical transformers. And it gets worse. It's an astonishing 80 weeks for medium voltage switchgear. For the hyperscalers, the massive tech companies dropping billions to build these facilities, these aren't just minor inconveniences. These delays threaten to strain billions of dollars in deployed capital simply because a facility cannot turn on without this exact equipment.
What's happening is that silicon roadmaps now totally dictate physical infrastructure. Because the architecture of GPUs and custom chips evolves annually, equipment suppliers have to directly co-engineer their products with the chip makers years in advance. We're seeing massive shifts, like moving to 800-volt direct current distribution right at the rack level. That means heavy industrial-scale power is flowing directly to the servers. If a supplier's product line isn't iterating at the exact same breakneck speed as the semiconductors themselves, they're going to be entirely locked out of the market. Let's look at the foundation of all of this in Section 3, the power grid reality. To really understand the scale of the power problem, we have to look at the baseline. According to the World Nuclear Association, global nuclear power plants supplied 2,667 terawatt-hours of electricity in 2024. That is an almost unfathomable amount of energy. But, as we discussed earlier, the demands of continuous 24/7 AI inference are growing so fast, they are threatening to overwhelm that existing capacity entirely. Right now, nuclear energy provides roughly 9% of the world's electricity, and that's driven by 438 operable reactors spread across 31 countries. So why is nuclear so critical to the AI story? It comes down to corporate promises. Tech companies have made massive net zero carbon pledges. They absolutely cannot power these giant new AI data centers by burning coal without completely destroying their climate goals. They need dense, reliable, 24/7 baseload power. Wind and solar are great, but they're intermittent. The wind doesn't always blow and the sun doesn't always shine. Nuclear is the second largest low-carbon power source on Earth, making it uniquely suited to feed the relentless, non-stop appetite of generative AI. The globe is already scrambling to add generation capacity to meet this looming deficit. Just look at the physical construction starts scheduled for the first quarter of 2026 alone. We're seeing Shuai in China in mid-January, Kursk in Russia at the end of the month, Paks in Hungary in early February, and Kaiga in India by March. Globally, there are nearly 80 reactors under construction right now, and over 100 more planned. The world is quite literally moving dirt and pouring concrete today just to ensure we have the grid capacity to run the AI models of tomorrow. And this aligns perfectly with long-term macroeconomic targets. The International Energy Agency's net zero emissions scenario maps out a strict requirement for global nuclear capacity to reach over 1,000 gigawatts by 2050. Stabilizing the grid while simultaneously meeting this historic new electricity demand requires an absolute renaissance in heavy physical infrastructure. Let's pull this all together in Section 4, the Infrastructure Investment Supercycle. McKinsey has laid out a clear 5-step strategic playbook for industrial CEOs who want to capture their share of this hyper-growth market. Step 1, you have to co-engineer directly with the tech players. You can't just sit around waiting for traditional requests for proposals anymore. Step 2, build the flexibility to scale production quickly from pilot to high volume. Step 3, organize your business end-to-end around the data center customer, rather than operating in siloed, outdated product lines. Step 4, de-risk your capital investments through strategic partnerships. And Step 5, treat talent as a strategic investment. The engineers and field technicians needed to build and service these highly complex sites are in incredibly short supply right now. The message from the data is undeniably clear. The window for industrial suppliers to secure leading positions in this great data center build-out is rapidly narrowing. Legacy companies that sit back and wait for traditional, slow-moving procurement cycles are going to wake up and find that a multi-trillion-dollar opportunity has completely passed them by. The big winners in the AI revolution might not just be the software coders out in Silicon Valley. They're going to be the forward-thinking industrial manufacturers who can actually deliver the steel, the cooling systems, and the power. We are officially transitioning from the conceptual software phase of artificial intelligence into the heavy industrial phase. As the AI supercycle shifts from lines of code into steel, dirt, and uranium, you really have to ask yourself, how is your portfolio positioned for the physical reality of the grid?